Alright, this demo is going to show you how you can use agents as an analysis tool. So I'll just start running the simulation and I'll kind of talk as it goes. So this is an analysis that I found in this paper by this guy Carranza. It's a really good paper, and in it he describes an algorithm where he uses the concept of kind of forgetting to drive the intelligence of the analysis. And so in this case he's saying if you see a potential for a collision, slow down, otherwise speed up. And so what this causes is, if in this case where I have my this is a building I did, if you say, slow down if you see potential for a collision, what you'll get is kind of the agents will tend to stay longer in the areas where there's more potentials for collisions, for things like kind of plaza spaces. You can see where these little arrows are lighting up. That's actually where they're saying there's a potential for a collision, and they're going to slow down. So they slow down where there's a potential for a collision, causing them to stay in that area longer, causing more agents to kind of be trapped in that area as well. And what you should eventually get is kind of a diagrammatic analysis of where the areas of interaction are. So this could be used to kind of discover or validate where you think the areas of interaction are for your architecture project. So I have this floor plan. It's actually easier to see if you just have showing the agents trails, and in this case I actually have two different systems set up here. And the kind of concept for this building was a large part that there would be kind of an area for the public to be, and then an area for the students. This was a school, so the public had to be kept out of the school, obviously, but we wanted some level of kind of interaction for the public to kind of see what the students were doing. It was like a vocational school about growing plants and kind of urban gardening. So that you can see that the green arrows are where the public was allowed to go. It's kind of this white area, and then the students were allowed to go in this gray area. And so in my model, when I set it up, there's this kind of larger, this whole area is where the students are allowed to go, but the public is only allowed to be on this surface. And so I have two systems set up, one where that has this environment and one that has this environment. And so you can see that the students are in blue, and we could see that only the students are allowed in this area over here, but everyone is kind of coming from the directions they would be coming from. So in this sense I have emitters set up at the stairways and at the entranceways to the walkway. And so we see the students in blue and the public in green, and we can kind of get a sense of where the interaction points are, where the most interaction is happening between just the public, between the public and the students, and also with just the students. And so you can get kind of a rough idea of to validate your concept of where these different groups of people are going to be interacting. So I think I'll just let this play out. So we've already done 1,000 iterations, and we can see that indeed kind of this area has a lot of interaction happening. See, there tends to be a lot. The agents stay here longer, as well as this area where it gets pretty narrow. You can see both of them tend to be in this area. You can see also the students will eventually enter the school and kind of explore a little bit. It's important to note that I'm not calling these kind of the actual behavior of the people. This is more an analysis, kind of using this abstraction of agents. So it's just saying, wander around the space, slow down if you see a potential collision. So you tend to stay in the areas where there's a potential for collision. It's kind of a really simple rule set. The script, can get a little wiry, but it's honestly not as complicated as it looks. These are just, setting up my emission points, contain within the environment, wander a little bit. If the current velocity is larger than maximum speed, set it to be the maximum speed. If its velocity is less than the minimum speed, set the velocity to be the minimum speed. So these guys are always moving. They're never going to stop completely. And if the current velocity is less than maximum speed, then speed up. So they speed up by this amount. And then slow down if there's a potential for collision. So here I'm not even applying this avoid unaligned collision force. I'm just using it to determine whether or not I should take their current velocity and then slow it down by a little bit. And I have two systems set up like this, and I know it looks it looks really complicated, and it took a while to set up. But if you can understand the rules, then you should be able to kind of work through this method. Alright, so this is it after about 5,000 runs. That took about 15 minutes to run, a little bit better than the 8 hours it took to run the 10,000 iterations of Carranza's program, which I wish I had a date when that was written. It was probably written a few years ago. Many years ago is what I mean. You can see you can get, you iterate a little bit faster, kind of the modern computers and a few of the optimization techniques that Quelea uses. But let's see if we learned anything. I'm going to bring this back over here. And let's look at our floor plan. This is better. All right. So let's look at them individually. Turn off the students. So this is where the public walked around. Again, this isn't really how people move. This is just kind of an analysis technique of an abstraction. But we can look and see kind of where they tended to kind of interact more. We can see that this area has a lot of interaction, as well as this area as well. They even get into this little workshop demo area. This is like a theater that the public is allowed to access the upper levels of, a cafe space. So we could start to see, where they are interacting. And of course, here where there's kind of a big intersection of, different entryways, we get a lot more interaction. And how about students? So the students had a little bit more area to explore, and you can see they definitely do, they stay on the walkway a lot, but they also get into the school, and we can see, thankfully, they do tend towards this cafeteria area as well as these lounge areas. This is really analysis of kind of, what's the most accessible and where the interactions occur. So you get a general sense. This is that entranceway. Again, this is the only way into the school. and you get a little sense these are lounge areas. Thankfully, they're going in there. Amazingly, they managed to avoid the bathrooms, which is cool, except for this. And then if we look at them together, we can see, where the two, interact with each other the most. And clearly it's kind of this area around here, as well as this kind of plaza intersection area. So that's it. Hopefully that wasn't one of the more confusing demos, but I think it's a kind of a good showing of kind of the diversity of things you can do, and start thinking about how you can use these forces in your analysis. So in this case, when I use this collision avoid unaligned collision force, I don't even apply it. I'm saying don't apply this force. I'm just kind of using it to see if this force should be applied, then actually just decrease their current velocity by this amount. So you can get really creative with how you're using these forces and how it influences their behavior. That's it. I'll just leave you with that, and I'll see you in the next video.